Good morning, students. Today we are going to study the remaining numericals based on the open feed water heater and closed feed water heater and multiple feed water heater. So today the topic is the all feed water heater having its numericals. The first of all, before going to start the numerical, I will revise again what is the feed water, what is the open feed water heater, what is the closed feed water heater. The first of all, feed water heater means nothing but the regenerator. It is device. It is a device where the feed water heated by regeneration is known as where the feed water heated by regeneration known as the regenerator or feed water heater. It has two types. One is the open feed water heater and the closed feed water heater. A feed water heater is basically the heat exchanger. It is a heat exchanger where heat is transferred from the steam where the heat is transferred from the steam to the feed water either by mixing the two steams, that is open feed water heater, or without mixing them, that is closed feed water heater. That means nothing but the feed water heater, nothing but it acts as a heat exchanger. Then we discuss about the open feed water heater. A open feed water heater, that is nothing but the direct contact water heater, is basically a mixing chamber where the steam extracted from the turbine mixes with the feed water exiting the pump. Ideally, the mixture leaves the heater as a saturated liquid at a heater pressure. That means we have to discuss about the some important information regarding the open feed water heater and closed feed water heater. In case of the closed feed water heater, in this feed water, the heat is transferred from the extracted steam to the feed water without mixing takes place. A closed heater system requires only a single pump for a main feed water heater, regardless of the number of heaters. We can conclude this topic. That means the higher the number of heater used in the higher will be the cycle efficiency. That means how much amount of how many heaters are used. What is the importance? That is the higher number of heater used, the higher will be the efficiency. When we are using the higher heater, high number of heater, that we will get the high efficiency. In another way, we can say that an increase in feed water temperature may in some cases cause reduction in the boiler efficiency. It may be possible, suppose the water heater is increases drastically, that may be the reduction of reduction in boiler efficiency. So the number of heater gets optimized. The five heaters are oftenly used in practice. That means the maximum five heater can be used to improve the boiler efficiency. Then go to the numerical section. This is the some in revision of the topic. Therefore, we get the numerical belong to the open feed water heater. The first one, the steam at a 30 bar and 350 degrees Celsius is supplied to steam turbine in a practical regenerative cycle. In practical regenerative cycle, and steam is blend at 4 bar. The blend steam comes out as a dry saturated steam and hits the feed water in an open feed water heater to its saturated liquid state. The rest of the steam in the turbine expands to condenser pressure of 0.1 bar. Assuming the turbine efficiency to be same before and after bleeding, determine first one the temperature, the turbine efficiency, second the steam quality at inlet to the condenser, third one mass flow rate of the blend steam per minute, mass rate at the turbine inlet, and fourth one again you have to find out the cycle efficiency. That means is the this first of all you have to identify the numerical. That means this numerical belongs to the again the open feed water heater. In this case, what happening? The steam having a pressure 30 bar, having a temperature 350 degrees Celsius is supplied to turbine. That means the steam having a pressure 30 bar and 350 degrees Celsius temperature enter into turbine section, and then the steam is blade at 4 bar. That is this is the region. First of all, you have to draw the TS diagram, you have to draw the saturation curve, and you have to locate the point 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 to 1. So in this case, what happening? That means the steam is enter in the turbine section. This steam is blend at the 4 bar, and the blend steam comes a dry saturated steam, and heats the water, and the steam expands condenser pressure 1.0.1 bar, and assume the turbine efficiency same uh, before and after blending. That means this is the area that is the boiler pressure is there. This is the second is the blending pressure is there. This is the condenser pressure. There three lines are there. That is, first of all, you have to draw the saturation curve and you have to locate the points. First of all, that means in turbine section pressure is 30 bar. In blending section the pressure is 4 bar, and the condenser section 0.1 bar. The from this data you have to find out how much amount of turbine efficiency, find out the steam quality at inlet, what is the, and then mass flow rate and the cycle efficiency. The first of all you have to go to the turbine section, and from turbine section the pressure is P2 equal to 30 bar, temperature 350. Again you have to use the steam table, and from steam table you have to find out the values. First of all, that means the temperature 350 degrees Celsius, that means the temperature is more than 100%, that the steam is superheated. Then you have to go to superheated section. From this one, this is the the P2 is the in turbine pressure. In the P3 is the 4 bar, that is the condenser pressure. Like P3 is the 4 bar, that means this is the blending pressure, and this is the condenser pressure, part 1 condenser pressure. And you have to find out this value from the enthalpy value. You have to find out in this case P3 S3 P3 point, that the blending section you have to get in the enthalpy value. S3 means enthalpy value 2737.6 kJ per kg for getting the from steam table. Then go to the from superheated steam table, and you have to find the value S2 S3 equal to P3 equal to 4 bar 2737.6 kJ per kg. What is that means? In this case you have to go to this one 3.3, and this is 2. This is the point in which you have to enthalpy is located, and therefore you have to find enthalpy at point 30 bar and 350 degrees is again from steam table. You will get the values from steam table 3117.5 kg per kg. This is the nothing but the enthalpy, and you have to find the entropy also. S2 equal to 6.7471 kg per kg Kelvin. This is entropy getting from this one. Then at pressure 0.1 bar, that is the nothing but the condenser pressure. From condenser pressure it is indicated by the 5 H5 point. That the condenser pressure is given the 5 point. Okay, and you have to find H4, and H4 P5, that is the in this case 0.1 per 191.8. This is the enthalpy, and S7 4 bar 604.7 per kg, that is from the S7. The S7 part is there in this case. And then you have to find out process 2 3 isentropic. That means you from the diagram 2 to 3 line is perpendicular to the entropy. This is the S line, that is the entropy line. This is the temperature line, and then S is perpendicular 2 to 3 line, that is telling entropy at point 2 equal to entropy at point 3. Therefore you have write down S2 equal to S3. Then put the values and put the equation, and from this equation you are getting the value x3. This is dryness fraction you are getting in this case. That is the, in this case is this region the dryness fraction of steam x3 s equal to 0.971. This is 0.971. Then from this value dryness fraction you have to find out the value of enthalpy. Therefore H equal to H of x HFG. You have to put the values and put the formula, and you will get S3 enthalpy at point 3 2676.25 kJ per kg. You are getting the value of H3 enthalpy. Then go to the process 3 to 4. Again go to 3 to 4 process, and from 3 to 4 process what is happening? Again the entropy is changed, because the S3 and S4 line is perpendicular to this entropy line. Therefore S3 equal to S4, that is entropy at point 3 equal to entropy at point 4. Then go to the process 3 to 4, put the formula again SF Hg SF Hg equal to SF plus X SFG SFG. Therefore put the formula, and you will get the X4. 0.834. That means this is the region 843. This is the region stream having a dry fraction 0.843. And then from this X3 dynamics fraction, you have to find out the value of H4 enthalpy at point 4. Again, the same formula Hg equal to Hf plus XHFg. Put the values in this case, and you will get H4 to 183.8 kilojoule per kg. That is the point H point. You have to get in the this point. You are getting the enthalpy point, and then go to the you are getting the H4 values, you are getting the H4 value, then finding out the condition in the given numerical, the turbine efficiency before blending and turbine efficiency after blending is same. Then you have to equate this equation. First of all, you have to find out the turbine efficiency because blending S2 minus S3, S2 minus HS3. That is again go to S2 and S3, S2 minus S3 and S2 minus HS3. You have to put the formula from the diagram and you have to put the values and you will get the turbine efficiency 0.86. Then you have to equate this equation and you have to apply again 3 to 4 condition. Again S3 minus H4, S3 minus H4S, 4S, and put this from diagram. You put the values, you will getting the value H4 2261.33 kilojoule per kg. You are getting the enthalpy at point 4. Then for we are getting the H4, from H4 you have to find out the X4, that is the Dias fraction. Then H4 equal to HF4, X3 HF, that is the H means that is H equal to Hg equal to HF plus XHF. This is the formula, basic formula. And put the values from the equation and you are getting the values X4 0.864, and this is the dryness fraction at point 4. The dryness fraction at entry to the condenser. This is X4 is nothing but the dryness fraction at the entry to the condenser. Listen, this is the point X4. This is the entry into the condenser section. Therefore, this is the X4. The entry into the condenser. This is the line indicate the condenser line, and this is the condenser line. Therefore, dryness fraction at the entry to the condenser X4 equals 0.865. Okay, and then go to the third point. Check a third point to find out the let m kg of steam is blade. Apply the energy balance to feed water heater. Whenever the numerical belongs to the open feed water heater or closed feed water heater, that time you have to consider the steady flow energy equation, balance equation. Therefore, you have to in this case you have to consider m kg of mass steam is blade. Then you have to this equation m into S3 plus in bracket 1 minus m in bracket come to S3 is equal to S3. This equation can be developed from this diagram. Developed from this diagram. This is the area to be taken to form the diagram, and then from the diagram we have to get in the equation. You have to find out the pump work. Pump work means again 6.5 S6 S6 minus H5. This is the area in which the pump work done. This is the area in which the pump work indicated. Therefore, pump work equal to S6 minus H5. Therefore, we integration dp. You have to put the values. We are getting 0.394 kJ per kg. And from this equation, you have to find S6 and 0.394 plus 191.8 equal to 192.18 kJ per kg. And we are getting the value of S6. Put the value of S6 and then this value of S6 and put the other values, you are getting the value of M, the mass of stream blend. Therefore, mass of stream blend equal to 0.162 kg. And then again the same condition apply for pump second H1 minus H7. Again go to diagram H1 minus H7. This is the diagram. This is the pump 2. This is the area indicated the pump work 2. Therefore H1 minus that is the P1 H1 minus H7 equal to VDP integration VDP. Then again find the value pump work equal to 2.82 kilojoule per kg, and then from this one you have to again find out the value of H1 equal to HF plus HFG, and then put the values. We are getting the H1 values 6060 kilojoule per kg, and then finally you have to find out the cycle efficiency. Finally find out the cycle efficiency. Again the turbine work minus pump work you are divided by the heat supplied. Put the equations and find out the put the values. We are getting the cycle efficiency 0.31%. 0.31%. That means in this case, the dryness fraction at the entry is the new parameter to be discussed here. That is the dryness fraction at condenser section, and then you have to find a cycle efficiency. and this is the end of the first numerical. Then go to the another numerical, that is, in an idle reheat regenerative cycle, the high pressure turbine receives steam at 20 bar 300 degrees Celsius. After expansion to 7 bar, the steam is reheated to 300 degrees Celsius and expands in an intermediate pressure turbine to 1 bar. A fraction of steam is now extracted from feed water heating in an open type feed water heater. The remaining steam expands in a low pressure turbine to a final pressure of 0.05 bar. Determine first one cycle thermal efficiency, second specific steam consumption, and third and last one quality of steam entering the condenser. The first of all, again you have to read the numerical and you have to identify the numerical which type. That is again the numerical belong to reheat regenerative cycle having a addition of open type feed water heater. Then the first of all, in this case what is given, the pressure turbine receives steam 20 bar 300 degrees Celsius. Again the turbine receives the steam having the temperature 300 degrees Celsius. That means the temperature of steam is more than 100 degrees Celsius. That means the steam is superheated. After expansion to 7 bar, the steam is reheated. After expansion, the reheated steam again reheated to the 300 degrees Celsius at 7 bar and they expands in the intermediate pressure 1 bar. And after that, the steam expand the low turbine in 0.05 bar. In this case, the different section, the pressure is having a different pressure in a different section, and in this numerical you have to find out first one is the cycle efficiency. First one, and second, steam consumption. How much amount of steam consumed in the during the cycle, and third one, quality of steam entering the condenser. There again the dryness fraction of steam and entering the condenser. The first of all, you have to draw the TS diagram, and then you have to again draw the saturation curve. You have to locate the point 1 to 2, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. And then you have to look at the temperature. Do you look at the temperature? You look at the pressure lines. Pressure lines. The from this diagram, again use of steam table is used. The in this numerical again steam table is used. From the steam table, you have to find out the values at 20 bar and 300 degrees Celsius. Go to the again superheated steam table, and from superheated steam table you have to getting the value enthalpy at point 2. This is the point 2. The enthalpy of point 2 you are getting 3025 kilojoules per kg, and you have to find the entropy also. S2 equal to 67696 kilojoules per kg. You are getting the enthalpy value, entropy value at point number 2. This is the turbine section. Then process 2 to 3 isentropy. That means entropy at point 2, entropy at point 3 same. That is the line 2 to 3 is perpendicular to this S diagram. That is the isentropic process. Therefore, you have to write S2 equal to S3 and put the equation again. S2 value is given in this case 6.769696 equal to 190.9918 plus x3 in bracket 4.7134 bracket complete, will get the x3, and from this equation you have to find out the dryness fraction at point 3. You are getting the dryness fraction at point 3. After that we have to go to the state 3, and you have to at state 3 the steam consider the dry saturated. Therefore, you have to go to at 7 bar pressure from steam table and take the value S3 from the steam table 2762 kJ per kg, and then you have to take the H4 values having 7 bar pressure along with the temperature 300 degrees Celsius. You are getting from steam table 3059.8 kg per kg, and in entropy S4 equal to 7.22997 kg per kg. You are getting this value from that one. Then go to the process 4 to 5. Again go to process 4 to 5. What happening in this case? 4 to 5 again the perpendicular line to the entropy. That means the entropy at point S4 4 point and entropy at point 5 is same. Therefore, we can write down S4 equal to S5. and again you have to put the values s4 in this equation, and you write the equation. You are getting equation, and you are getting find after solving this one, you are getting the value of x5. The dryness fraction at point 5 equal to 0.99. Again go to this point 5. That means at that point the dryness fraction of steam is 0.99. And then after that again go to the after 5 point, after h5 hf plus x4 sfg4, and we have to find out, we are getting the x5, then we are automatically easily find out the value of enthalpy at point h5. The h5 put the values, and you are getting the point enthalpy 2652.9 kilojoule per kg. That means you are getting the intra enthalpy value at point 0.5. We are getting the enthalpy value at point 0.5. You are getting h5. After then we are getting the h5. Then again go to the process. Again go to the process 5 to 6. We are getting the dryness fraction at point 0.5. We are getting the enthalpy at point 0.5 already given. Then go to process 5 to 6. What is happening? Then 5 to 6, again the line is perpendicular. 5 to 6 is the entropy line. That is the entropy at point 0.5 equal to entropy at point 0.6 is same. Therefore S5 equal to S6. S5 equal to S6. And then again put the values. You are from this equation, we are to getting the dryness fraction at points x6, that is 6 equal to 0.862. And from this h62 dryness fraction, you are getting the value of s3 s6, that is the enthalpy at point 6. And put the values, put the formula values, 2226.1, 2226.1 kg per kg, you are getting the s6, that is the point 0.6. You are getting the dryness fraction, you are getting the enthalpy at point 0.6 point. Okay, then go to the after point, after covering the point 4, 5 and 6, and then go to the point 7. At point 7, what happens? Again the pressure is different, 0.05 bar, and go to steam table, and then you have to getting the values. H value S7 137.8 kJ per kg. In this case, neglecting pump work, and H at equal to S7. H at equal to S7. Again go to 7 point. This is the line 7 to 8 line, again perpendicular to that one. Therefore, enthalpy. Therefore, we can write down enthalpy is also same H, and H at equal to S7. Again, on the in case of the pointer 9 to 2 to 9, again to go to the line 2. This is the line 1 to 9, 1 to 9. Therefore, you can write down the H1 equal to H9, because neglecting pump work, W for WP1 and WP2. Therefore, we are getting the value H9 at a pressure 1 bar. We are getting 417.5 kilojoule per kg, or this value taken from steam table, and this is the H7 value also given from the steam table, because having the pressure 0.05 bar. The pressure is different, point is different. Then whenever the numerical discussion, uh, whenever the numerical belongs to the feed water heater, that time you have to consider the steady flow energy equation. Therefore, in this case, again write down applying the energy balance equation. From this equation, m into h5 plus in bracket 1 minus m bracket complete hg h8 equal to h9. This equation is considering from the diagram. You go to this diagram, and from the diagram you have to develop the equation and this equation, and therefore put the value of h5, put the value of h8, put the value of h9, that is the enthalpy at point 5, enthalpy at point 8, enthalpy at 9, and you will get the values mass equal to 0.111 kg per kg of steam. That way you are getting the value from this steady flow energy equations applied to feed water heater. We are getting the mass of steam equal to 0.111 kg per kg of steam you are getting. Then find out the condenser efficiency, NC. Condenser efficiency, that way again the S2 minus S3, S2 minus S3, go to this S2 minus S3, this is the area S2 minus S3, then H4 minus H5, H4, H4 minus H5, H2, H2 minus H3, H4 minus H5, and then plus 1 minus M, H5S6, 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 this is the area. And by developing the equation and divide by S2 minus H1, H4 minus H2, S2 minus H1, S2 minus H1, S2 minus H1, that is the heat addition text, H2 minus H1, H2 minus H1 equation, and H4 minus H3. H4 H4 minus H3. That this is the area that means what happening in this case the heat addition takes place. This is the region in which the heat addition takes place. There we are divided by this one. We are getting 0.35. For the all values, you are getting 0.35. That is efficiency, condenser efficiency 0.35. Then you have to steam consumption, SSC 3600 divided by W net. Put the values, and you are getting this steam consumption 3.57 kg per kilowatt hour. They are getting it. Then after that, we have already find out the values x6. The x6 is nothing but the quality of steam entering the condenser x6 equal to 0.862. Listen, S6. And this is the point in which the steam is entered into condenser section because this line indicates 6 to 7 line indicate the condenser line. Therefore, X6 means nothing but the dryness fraction of steam entering the condenser. And this is the end of the second numerical. Then go to the another numerical. This is the last numerical of today's session. The net power output of a regenerative reheat cycle power plant is 80 megawatt. Steam enters the high pressure turbine at 80 bar 500 degrees Celsius and expands to a pressure P2 and emerges as a dry vapor. Some of the steam goes to an open feed water heater and the balance is reheated at 400 degrees Celsius at a constant pressure P2 and then expanded in the low pressure turbine to 0.05 bar. Determine the first one reheat pressure P2, then mass of blend steam per kg boiler steam, then steam flow rate in high pressure turbine, cycle efficiency, neglect the pump work, sketch the relevant lines on HS diagram and assume the expansion in the turbine as isentropic. Again, this numerical belongs to feed water heater. So in this numerical, what is given in this case, the net power output or output of the cycle is given. That means in this case, the power output of the cycle regenerative cycle is given 80 megawatt. The power output also given in this case. The steam enters a high pressure turbine. High pressure turbine, the pressure is 80 bar and 500 degrees Celsius. That means the temperature is more than 100 degrees Celsius. That the steam is superheated. Therefore, the turbine section, high pressure turbine, the pressure is 80 bar and 500 degrees Celsius and expands the pressure P2, a dry vapor, and some steam to an open feed water heater. The some steam is sending from the high pressure turbine to the open feed water heater, and in this case, the reheated at 400 degrees Celsius. Again, the steam is reheated at 400 degrees Celsius at constant P2, and then the steam again expanded in the low pressure turbine 0.05 bar. That means in this case, the two turbine is there, a high pressure turbine and low pressure turbine. In high pressure turbine, 80 pressure bar and 500 degrees Celsius. In low pressure turbine, 0.05 bar. And reheated section, 400 degrees Celsius, 400 degrees Celsius reheated, steam is reheated. And then in this case, what is to be determined? The first one, reheat pressure. How much pressure? At which pressure the steam is reheated at P2? That is P2. And what is the mass of steam? Mass of steam blending per kg of boiler steam. How much amount of steam is blending? And then how much amount of steam flow rate develop in the high pressure turbine? And lastly, we discuss about you have to find out about the cycle efficiency. Again, first of all, you have to draw the TS diagram. And from TS diagram, you have to draw the saturation curve, and then you have to locate the point 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 1. Again, this is this area, this line indicate the boiler pressure that they go into turbine. This is the reheat section, regeneration second, and last one the condenser line. And from this diagram, you have to locate the point. And in this case, what is the given input is there? The power output of the cycle is given 80 megawatt. That is the 80,000 kilowatt is given power. Pressure P1 80 bar, temperature T2 500 degrees Celsius. P2 is not given, reheat pressure is not given. Therefore, you have to determine temperature T3 is given, P3 is given 0.05 bar, Mass of steam not given. Mass of steam, how much amount of mass steam consumption, don't know. And you have for cycle efficiency. The first of all, you have to concentrate it, the 80 bar and 5 degrees Celsius. Then go to the steam, you have to again use the steam table. From the steam table, you go to superheated steam table line. From the steam table line, point 2. This is the point 2, in which at which you have to find out the enthalpy at point 2. That is the S2 equal to 3398.8 kilojoule per kg. And entropy is the 6.767 to 62. You are getting the values from the at point 2 having a pressure 80 bar. Then process 2 to 3 is isentropic. Again go to this line 2 to 3, the turbine section. The 2 to 3 section, the line is perpendicular to the entropy. That is the entropy at point 2 equal to entropy at point 3. Then you can write S2 equal to S3. Therefore value of S2 equal to S3. Therefore 6.762 S2 equal to S3 equal to 6.7262 kg per kg. Then go to point number 3. At point go to number 3 for a given state, the point 3, the dry saturated steam. Therefore, S3 is equal to 6.7262. Then go to from steam table again, pressure having 6 bar from steam table. You are to getting 6 bar and we are getting the value of entropy. Then apply and then find out the by applying the using the linear interpolation, you have to find out delta P. You are getting 0.402 bar. Then you have to find this equation, you are getting the value P2 equal to 6 plus 0.6402 will get 6.402 bar. You are find out delta P and then you have to add plus 6 and you are getting this one. From stream table you are getting this one. 60 and from, because this value 63 value, from 63 value you have to go to stream table, you have to use the Moliere chart, you are finding out the value of 6 and for interpolation formula you are getting the difference and you have to add it, you will get the value of P2, the reheat pressure 6.402. Then at point 3 again the 6.4 is given bar, again point 3 you go to point number 3, this point, and from this point you have to getting the enthalpy from this one from steam table. Again from steam table you are getting the value of Ag, that with the enthalpy, this is the entropy at 6. Then at point at pressure 7 bar you are getting the point value of entropy, but you are finding out the value of 6.4, but 6.4 is not given in the steam table. Therefore you have to find out the value, take the interpolation of that one, and for 6.5 6.4 bar you have to take the interpolation, apply the interpolation formula and you are getting the S3 equal to 2758.1 kg per kg. Then at the same time you have to go to point 4, H4 equal to H 6.4 bar 400 degrees Celsius. Again go to the point number 4. This is the point 4. From this point 4 you have to determine the enthalpy values having a temperature 400 degrees Celsius. Again go to steam table and then from steam table you have to superheated zone. You have to put the values for P equal to 6 bar, you are getting the enthalpy value, entropy value. For 7 bar this is the enthalpy value and this is the entropy value. And again interpolation you are getting the value of H4 623269.96 kg per kg and you are getting the value of S4 equal to 7.6790 kg per kg. This is the entropy value. And then again look at the process 4 to 5. Again go to the diagram 4 to 5. 4 to 5 line is perpendicular to the entropy line, that is the entropy at point 4 equal to entropy at point 5. Therefore we can write down S4 equal to S5, S4 equal to S5. You are already finding apply the equations for SF5 means SF5 plus X5 SFG5. Then put the equation and put the equation, you are getting the value of X5, the Dyna's fraction at 0.5, and then from Dyna's fraction 5 you are getting the enthalpy at zero point 0.5. H5 equal to that means HF plus X5 SFG5. Now put the values, you are getting H5 equation, that is the again this is the point. This is the point, you are getting the X5, then automatically you are finding out the H5 enthalpy by formula. H5, X5, X4, X5 is already given, and from the X5 we are getting the value of H5, that means the enthalpy point S5, that S5 equal to nothing but the 2342.41 kJ per kg. Then go to the point 6. At point 6, having a pressure for 0.05 bar, we are getting the value 137.8 kilos per kg from the steam table. And then and go to the S7 point. S7 S6 is equal. WP1 is neglected. Again go to 6 to 7 point. 6 to 7 point, pump work is neglected. Therefore, S7 6 point line is perpendicular to that one. Entropy. And you have to consider pump work is neglected. Therefore, enthalpy is same. Therefore, S7 equal to S6. At the same time, you can consider for the WP1 H1 equal to H8. Again, this is the pump work is neglected. Therefore, H1 equal to H8. And this equation, and where the value taking from that one, um taking the value of this one, S7 S6 equal to same, that is 681.1 for H8, and H1 equal to, no, H1 S5 equal to S6 value is 137, and H8 equal to H1, that is the 681.1. Whenever the discussion of the feed water heater, we can consider the again steady flow energy equation, and this equation can be taken from the diagram, because this is the area the steam is entering from the turbine to reheat section, heat water section, regeneration. Again, the steam is entering into the condenser section, and this is the region. And from this region, from this area, you have to developing the equation m into S3 plus in bracket 1 minus m into S7 equal to H8. Put the all values and we are getting the value of m. The mass of steam 0.313 kg per kg of steam. Then we are getting the mass of steam. We have to find out the W net. Why we are finding out W net? Because we are finding out the steam flow rate. Therefore, W1 equal to nothing but S2 minus S3, the pump work. Just put the values 640.7, S2 minus S3. Again go to diagram, S2 minus S3, S2 minus S3. Again, and then go to this one, find out the W2, 1 minus M, H4 minus H5, H4 minus H5. This is the region, H4 minus H5. This is the region. Pump for pump work 2 to 3, and pump second 4 to 5. And from this one, you are getting the value, put the values, and you are getting W equals 637.2. After that, we have to find out W net, total work net, that W plus W2, pump work 1 and W1 and W2. We are getting the W net. Then you have to find steam flow rate through HP, high pressure turbine, power upon W net. Total power is also given in the numerical, 80,000 kilowatt divided by 1 to 77.9 equal to 62.6 kg per second. So you are getting steam flow rate. Then finally determine the cycle efficiency. How to determine? Because again the cycle efficiency is nothing but the work done upon the Q heat supplied. Then you have to find out again QH. QH you are finding out from the diagram 3069.35, because S2 mass H1 and S4 mass S3. This is the area in which what happens, the heat addition, and heat addition, yeah, that means the H2 minus H1, heat added, heat addition S2 minus H1, S2 minus H1, again go to S2 minus H1. This is the heat addition area, the boiler section, S2 minus H1. And then second point is the H4 minus S3. The H4 minus S3 is nothing but this is the reheat section. The heat is added additionally. This is the 4 to 3 and 1 to 2, in which what happens, the heat addition takes place. Therefore, you have to heat added the H4, H2 mass, write down the value of this one, addition of the 2, addition of 2, we'll get the values, addition of 2, we get the values this one, QH equal 3069 by 35 kJ per kg, and put cycle finite cycle efficiency W upon heat supplied. Therefore, put the values and we'll get the 0.42. That is 42% we are getting the cycle efficiency. This numerical also the a different criteria having a different sections. In this case, heat addition area, power output is given in the numerical. This is a different numerical in this case. And this is the end of the today's session.